We have already defined DFA, and rigorously we have talked about this transition function. So what is it? It takes a state and a symbol, and it gives you a state. So since it's a function, and it should do that for all states and all symbol, right? So now sometimes it is easier or much more cleaner if we treat this function as a partial function. So what do we mean by partial function? That is, for some input, for some q and some symbol a, this delta qa can be undefined, okay, for some pairs. So in the transition diagram, how will it look like? So look at this diagram. So this diagram. Now here from Q0 on symbol A, you have a transition. But if you are in Q0 and if you try to process input symbol B, then there is no transition available. So your machine will get stuck. Okay. And the input string, whatever is left of it, and everything will be rejected. So we sometimes say that there is no valid move, or okay, so this sort of jargon. So we already stated that there is no valid move for input symbol B from state Q0. So, and also, as I mentioned, if you see any input, okay, where while processing this input, at some point of time you come across say some invalid move, so then immediately you discard all the input. So this entire string is rejected, right? So if we give input string BAA, on the very first symbol, there is no transition, so this entire string will be rejected. So this entire BAA will be rejected. Okay. And with this interpretation of acceptance of string, you can easily see that this automata is nothing but something which accepts all the strings that begin with A. Okay, it's obvious from this construction that because it takes A and then it can take anything, and after that everything is accepting. Now here it is easier if we just leave the transition on B undefined. If we want to accept say this language, this can be accepted by a DFA with total transition function. By total we mean the normal, everything is defined. But then you have to figure out what you do with a transition from here with say B. Okay, so you have to somehow ensure that this, whatever this path is starting with B, this doesn't lead to any accepting state. So that is a extra headache that you need to care about. But with partial transition function, it's done in an easier way. So now, then does it introduce more complexity into the mathematics? If you are trying to prove something involving DFA or something, should we prove it for total function or partial transition function? If we prove it for total transition function, does that also hold for partial transition function? So the point is they are equivalent. Okay, equivalent in the sense we have already discussed in the second lecture maybe that two models are equivalent if they accept the same language. So here we have a theorem that if we are given a DFA with a partial transition function, so then we can construct another DFA with total transition function such that they accept the same language. And how do we do that? So the construction is very simple. We introduce one more state. So you see that this set of state, it's different from this in the respect that, okay, all the states of Q are here, but along with that we introduce just one more state, this dead state, say. And the transitions are also same. So whatever transition you have in your original DFA, you also have it here. But then in order to make it total, we need to define this kind of transitions because we have introduced this new state, right? So this says that if this transition on A is undefined in your given DFA, so then in your new DFA, you move to this dead state. Okay. So earlier in your DFA, there was no place to go on input symbol A from this state Q. So now all this situation is handled by the thing that here you go to dead state. And once you move to dead state, okay, so then no matter what input symbol you process, you remain in dead state. So that is a trap. It's also called a trapped state. Okay, so what will happen for this automata? So here all the transitions are defined for this thing on A and B. So here this transition is not defined. So here we will make this transition and move to the dead state, right? And this dead state is not part of the final state. So the final set of final state is same, right? We are introducing a new state, but that we are not including in final state. So this is not final state. So now this is a specific example, but it's easily seen that it holds for any arbitrary DFA. I mean, no matter how complex your DFA is, if there is no transition, from there you actually make a transition to dead state, this newly created dead state. And once you come to dead state, so no matter what input you get, you remain in dead state, and that's a non-accepting state, right? So you can easily see that since all the original transitions are also in the new DFA, so then if this path is defined, so this is delta hat, right? So this is extended delta, this is a string, you see. So if you have a path from state Q on this input string W in the original DFA, then you also have that path in the newly created DFA, right? And if that path leads to any final state in the original DFA, also in the new DFA, that will be same. They are same on if they are defined. Okay, so if this is defined, then they are same. This delta and delta prime agree on all valid moves. So here, in fact, I can say that this is equal to this. So this this QW is so this is equal to this delta Q W. Okay. If sorry, here we have delta prime. So if this is defined at all, so then they are equal. But if this is not defined, then that means there was a invalid move encountered while processing W, and in that case it will move to dead state and remain in dead state. So that's our proof. Now, as I said before, sometimes it is easier to use this sort of partial transition function. So if that is the case, we will use partial transition function. But without loss of generality, we can always assume that the transition function is total. If we require that. So suppose you are trying to prove some theorem about some language which is accepted by some DFA. So in order to prove that it is accepted by some DFA, you construct a DFA with partial transition function. And then for the later part of the proof, suppose you need that the function should be total. So then without loss of generality, you say that, okay, it's same. Now, so far we have seen certain examples of DFA, and we gave the language and we gave the DFA, and we said that okay, somehow you can prove. Now it's slightly harder if you are just given a language. Say if I give you this language and ask you to construct a DFA for this language. I mean, a priori we don't even know whether such a DFA exists or not. So we need to try out and figure out whether we can construct it or not. So now this is an art. I mean, it requires ingenuity. There is no hard and fast formula to do that. You need to solve each problem separately, but still some general guidelines help, and this is how you can approach many of the problems. So first of all, from the given language, you try to figure out what are the strings that are in the language, some specific examples, and some short input string, right? You try to see whether some length 1, length 2, length 3 input symbols are in your language. And depending on that, you try to guess some path, okay? Or some states that you require to handle these short strings. Forget about the general language, all the strings now. So that is the bare minimum. And once you have some of these states, so then you ask that, okay, you should have a start state. So this is a start state, okay, and this is any state that you think should be, sorry. Yeah, so this is start state, and this is some state that you think should be in your automata. Then you ask, what are the strings corresponding to this state? So each state corresponds to a set of string. What string? The strings that can lead to this state, right? So you make say some transitions, and starting from this 0, you go to this state Q. So then you ask, what are the strings that can get you to this state? So you somehow try to figure out some property of these strings, okay? Some more intuitive property than just this delta or whatever. So once you do that, once you have a bunch of state and you have some idea that, okay, in order to reach this state, some string must have this property. In order to reach this state, some string must have, say, this property. Okay. So then you try to figure out, okay, what if I append some symbol to this string, and then does this string satisfy this property or not? So if that is the case, then maybe there is a transition from this state to this state, right? Because this W had some property for which it landed up in this state, and then it took one more input symbol. So now we are talking about this string, and that has property P2. So maybe that should lead to P, because you somehow already guessed or figured out that the strings here should have property P2. Okay, so that's the general idea. So how does that apply to this specific problem? So this problem is the set of all strings that end with this AB. Okay, and this is these are strings over this alphabet. It contains only AB, right? So immediately you see that the string AB itself is in this language. So there must be, so since AB is in the language, there must be some path like this, right? You make a transition on A, then you make a transition on B, and then you should land in some final state. So this is doubly circled, so that means it's a final state, right? And there might be more than one final state, but as I said, there is no hard and fast rule, and you try to sort of figure out this property and what property the strings should have in order to reach something. So let's see whether we can make it work with just this one final state. So if that is the case, so then the strings that lead from Q0 to Q2, they are precisely the strings which are in this language, right? Because they are the strings that are accepted. So we need other states maybe, but at least this is our this is what we have. So this will correspond to strings which end with AB, right? So now if we fix on this thing, what are the strings that can lead me to this place? Okay. So then it follows that it will be strings which end with A, because then with B it can go here, which has this property. So you see I am addressing this issue. Okay, what property the strings should have. Strings corresponding to a particular state, not just final state. Now once you have this thing, and maybe here you say that all other strings perhaps leads to here, and again you cannot be sure at this point, but at least this will give you some guidance. So now if we fix on this thing, so these are strings which do not end with AB or A, because those are the strings here. So then you try to figure out the arrows. We already have these two arrows, and they are consistent with this interpretation. So now if you are here, so that means whatever your string you have ends with AB, and say now again you receive one A. Okay, so then it will be a string which ends with A. So then maybe from here you go back to here on A, right? So this transition I'm talking about. So if you have so here you have something like WAB, and then you try to figure out what happens with another A, and you see that this is a string which belongs here. So you take this transition, right? Similarly, you try to figure out what happens if you append, so instead of A, if you append B here. So then you see that it falls into this category, and you make this transition, and now you can put all these transitions. Now, as I said, this is not a proof that this will work, but now in order to prove, you have to use some induction. So whatever guess you made that this should correspond to this strings, this should correspond to this strings, and this should correspond to this strings. So this is the claim that you make in order to properly prove this thing. These are the claims that you make, and you prove this claim using induction on the input length. So yeah. So that proof part is necessary, but at least these are some behind the scene process which leads to this construction. And as I mentioned before, there can be different DFAs which accept the same language. So maybe somebody else thinks slightly differently and he comes up with another DFA. That is also possible. But that should be equivalent, because they all should accept this string, this language. So another example, again, so this is one example that I gave even without defining DFA, when I was talking about all possible all the automatas and grammars that we are going to study, the model of computation video. So you remember we talked about some function from strings to numbers, which somehow encodes integers, and so here we are considering binary representation. Okay, so W is string, and f of W is an integer. So what integer? So it's an integer such that this W is a binary representation of this integer. Okay, so again, so we said that f of 0 is 0, and f of 0 is also 0, and f of say 1 so this is in binary, so that will be integer 3, right? So this sort of thing. So there can be multiple representations of the same number, and is fine. And also we to make it slightly simpler, we consider this empty string to be the representation of integer 0. Okay, so now we want to accept all those strings over the symbols 0 and 1, such that the strings that we construct out of the symbols is a binary representation of some integer which is divisible by 3. So for all integers which are divisible by 3, their representation should be here. It's a if and only if condition. Now you see, since this empty string is accepted, so that means, so we are now focusing on say this point, so that means the start state itself, so this is start state, so start state itself should be a final state. So that is the only way a DFA can accept empty string, right? And again, if we at least go with the possibility that maybe we can make this work with only one final state, so then this state should correspond to all the integers such that they are divisible by 3, right? Now, as I said, you need some ingenuity to guess what the states are and what strings they correspond to. So each state corresponds to a bunch of strings such that those strings have some property. And here, instead of string, I'm using integer, but yeah, they are interchangeable via this function. So now, first of all, you notice that these are true, right? Because in binary, if you have some pattern, say this, so this is 5, right? So if you put a 0 after it, so then it is doubled, right? So, and if you put a 1 here, then it is doubled and then 1 is added. So these two things hold. So then maybe it's a clever guess that you consider also strings corresponding to integers which have modulo 1 and 1 mod 3 and 2 mod 3. So that completely kind of classifies all the possible strings. And then you try to put the arrows, and that is completely determined by this. You know that if you are here, so that means f of w is already divisible by 3, and if you put a 0, then f of that thing will also be divisible by 3. So that means there should be a 0, a transition on 0 which comes back to this place. Okay, so as I said, so after receiving, so 1 1 will be received, this is 3, and now if you put a 0, this becomes 6, so that should also be received. So on 0 you should come back to this. So yeah, according to this and this, now if you put all the arrows will look like this. Okay. So these are some guidelines to follow when you are trying to construct DFA from a given language, and the language is given by some property of strings. So later we will see that there are algorithms to convert NFA to DFA, or a different kind of NFA to NFA and then to DFA. So those are some mechanical process, but they generally produce very large number of states. So the number of states blow up. And then again there are algorithms to minimize the number of states, but you cannot just execute these algorithms on paper on say 5 or 6 states. So somehow if you're trying to directly come up with a DFA, you have to be clever. There is no way around, and with that cleverness this sort of insights help.